Right now, we are 8 billion people. But what if there were 100 billion inhabitants? That's a planet with a population 12.5 times larger. Is that possible? Will we all fit? Would there be enough food and water? And what about energy? According to United Nations projections, the world's population will peak in 2086 at around 10.43 billion people and then begin a decline. This means that 100 billion is beyond any realistic prediction. However, exploring an extreme scenario allows us to question the limits of the planet and properly assess concerns about overpopulation. Can we all physically fit? The first question to ask is, can we all physically fit? Or rather, can we fit with dignity? With a population of that size, the total global density would be 671 people per square kilometer. On the entire planet, only 9 countries have a higher density, and 2 more if we also include the special administrative regions of Macau and Hong Kong, which function almost as independent countries. And what is life like in these places? Bangladesh and Palestine have high levels of poverty. Bahrain and the Maldives offer an intermediate quality of life. And finally, most of the remaining countries have a high quality of life. They rank at the top in almost all desirable metrics, such as the Human Development Index, GDP per capita, and the Global Happiness Index. It's worth noting that 671 people per square kilometer is not an excessively high value. For example, Taiwan has a nearly equal density of 676 people per square kilometer, yet 2/3 of the island is relatively empty. Furthermore, in the 100 billion scenario, the vast majority would live in large cities, where very high densities can be achieved without losing quality of life. For example, in Barcelona, 16,000 people live per square kilometer, and there are no skyscrapers. In Seoul, there are 16,500, and in Paris, 21,000. In other words, there's plenty of space for urban, rural, and agricultural areas. Food and water. Which brings us to the next point, food and water. We know that water is a very sensitive issue, especially in places where it's scarce. But there is a solution to this problem: desalination. Fresh water on Earth represents just 3% of the total, and most of it is trapped in glaciers or underground. Meanwhile, 70% of the planet is covered in salt water, an abundant resource that can be harnessed through proper treatment. Today, producing 1 cubic meter of fresh water from the sea costs approximately 40 cents, of which about 15 cents is for electricity and 18 cents for infrastructure and financing. That is to say, it is no longer an inaccessible solution as it once was, and with the falling cost of renewable energy, its price could continue to drop. However, one outstanding problem remains: brine. For every liter of water generated, almost another liter of saline waste needs management. If discharged into the sea uncontrolled, it damages marine ecosystems. So technologies are being developed to extract useful minerals or safely return salt to the ocean. And as for food, if we look at the list of top agricultural exporters in 2022, we can see 3 countries much smaller than the rest: the Netherlands, Belgium, and Denmark. The first 2 benefit greatly from their key ports. Rotterdam, the largest in Europe, facilitates the import, processing, and re-export of agricultural products, while Antwerp, the second largest in Europe, fulfills a similar function. Even so, if we were to remove the numbers for those exports, both the Netherlands and Belgium would still appear on the list, as would Denmark, which achieves this without having a major port. So what's the secret of these small agricultural giants? There are 3 things they're doing really well. Technology. They've taken agriculture to an extreme level of precision, with greenhouses where they artificially control temperature, humidity, and light to maximize production. They've also implemented hydroponic crops and vertical farming techniques, allowing them to produce more with less space. Land use efficiency. Small countries, but they've optimized every square meter through crop rotation, agricultural automation, and the use of modified seeds to obtain maximum yield without depleting the soil. Investment in research and development. They have large research centers constantly working on new ways to make crops more resilient, improve production systems, and even integrate robots in the fields. Of course, so far we've only talked about vegetable crops, but they are the source of 83% of the entire planet's calories. And yet, they occupy only 16% of the area designated for agriculture, making them the most efficient use of land. 4% of agriculture goes to non-food crops, such as cotton or biofuels, and the remaining 80% is dedicated to livestock, from which we obtain meat, eggs, dairy products, and textiles. But even so, there's room for everything. Perhaps not so much for free-range grazing, but more for intensive livestock systems and efficient production in small spaces. This may generate pushback in some quarters, but lab-grown meat is advancing rapidly, offering a viable alternative that can reduce pressure on livestock and allow for a balance between intensive production and free-range farming. In addition, we also have our aquatic friends. Aside from the ocean, since 2013, aquaculture has become the main source of fish, boosting the farming of fish, mollusks, crustaceans, and aquatic plants. This sector has continued to expand, and in a world with 100 billion people, the solution could lie in developing floating facilities at sea or even underground. The energy challenge. So it's clear that we have enough space for everyone, and that such a large population could be fed and water supplied. The next complex issue is energy. With fluctuating prices, dependence on Russian gas, and the progressive closure of nuclear power plants, the future is currently uncertain. The first thing that comes to mind is solar energy. Currently, the efficiency of the solar panels typically installed is around 20%. However, the efficiency of various solar panels is constantly increasing. So let's do some calculations. Current global energy consumption is around 183,000 terawatt-hours. If we multiply this figure by 12.5 to reflect population growth, and then multiply this by 5 times more, assuming a more technological and energy-dependent world, total consumption would reach approximately 11.5 million terawatt-hours. So, if our efficiency didn't improve at all and stayed at 20%, an unrealistic scenario, we would need to cover 65.36 million square kilometers of our planet's area. That is, covering all of Africa, North America, and Europe. Obviously, this isn't an option. So let's assume a much higher efficiency of 50%, since our current efficiency record is 47.6% for one type of solar panel. This is extremely expensive, but it wouldn't be surprising if it became affordable in the future. In that case, we would need to cover a total area of 26.14 million square kilometers. That is, the entire North America. This scenario is still not feasible for generating 100% of global energy consumption. So, we'd better calculate how much solar energy can realistically contribute. That is, as is currently done with installations on rooftops, industrial buildings, public lands, or solar farms. A reasonable value in a very ambitious but feasible scenario could be around 3 million square kilometers of surface area covered by panels, which translates to a production of 2.63 million terawatt-hours per year, or approximately 23% of the consumption of 100 billion people. Obviously, we would need another energy source, but the solution to this problem may not be to everyone's liking. Nuclear energy. At the 2023 United Nations Climate Change Conference, 25 countries signed the declaration to triple nuclear power by 2050, with the goal of achieving net zero greenhouse gas emissions and keeping the global temperature rise below 1.5 degrees. And at the 2024 conference, 6 new countries joined the initial 25, bringing the total to 31. Now, if we analyze the list, we notice the absence of countries like Spain, Germany, Russia, India, and China. The last 3 are in the top 5 countries building the most nuclear power plants right now. So, they probably don't need to sign the commitment like those 31 countries. Germany in 2011 obtained a quarter of its electricity from nuclear power. But in 2023, they shut down the few remaining plants due to safety fears, strong public opposition, and a commitment to transition to renewable energy. In Spain, its 7 operating nuclear reactors generated 20% of the country's electricity in 2022. But it is gradually phasing out nuclear power due to political decisions, aging reactors, and a commitment to increasing renewable energy. But if we look at a map of Europe, we see that we are the exception, along with Belgium, among the only countries that intend to decommission their nuclear energy. The rest just build. And the same situation if we look at a world map. No other country plans to close its plants. If anything, they build more. We now know that of the nearly 200 countries in the world, only 3 maintain a clear stance against nuclear power. This means that in a hypothetical scenario with 100 billion inhabitants, nuclear power could be widely implemented without major political or social obstacles. So let's do the math. To generate 1 gigawatt of electricity, a nuclear reactor requires approximately 1 square mile, which is 2.6 square kilometers. By comparison, wind power needs 360 times more land to achieve the same output, while solar power requires 75 times more space. And in our assumption of 100 billion inhabitants, space is essential. A typical nuclear power plant produces around 10,500 gigawatt hours per year. To cover the remaining 77% of global consumption of 183,000 terawatt hours per year, or 141,000 terawatt hours, it would be necessary to build approximately 13,400 nuclear power plants. There are currently 400 in use and 60 under construction, so we are far from those numbers. But it would be feasible in our hypothetical scenario. And how much space would they take up? 13,400 square miles is approximately 35,000 square kilometers, equivalent to the size of Taiwan. And is there enough uranium for so many nuclear power plants? Currently, global uranium production is around 50,000 tons per year, with Kazakhstan as the leading producer, followed by Canada, Namibia, and Australia. However, annual uranium consumption exceeds 65,000 tons. The gap has been covered so far by reserves accumulated in past decades, when far more uranium was mined than was used. In other words, current production is already insufficient to supply the 400 plants in operation. So, how could we supply fuel for 13,400 plants without rapidly depleting resources?
First of all, we don't produce more currently because there's no need. Extracting much more than necessary would only lower the price of uranium, and that's not in the interest of supplier countries. Furthermore, it's estimated that there are nearly 8 million tons of recoverable uranium at competitive prices, concentrated mainly in Australia, Kazakhstan, Canada, and Russia. This translates into a supply equivalent to 160 years at current consumption. However, in a hypothetical scenario where nuclear demand increases dramatically, we would have to explore alternatives to expand the sector's capacity. For example, uranium dissolved in seawater represents a practically inexhaustible resource, since seawater contains approximately 3 micrograms of uranium per liter. If we consider the total volume of the oceans, the total amount of uranium dissolved in the sea is estimated at 4,500,000,000 tons. That's about 560 times more than what we have in known terrestrial reserves. Even granite, one of the most abundant rocks on Earth, contains uranium. The same granite you may have on your countertop has traces of this element. Although its concentration is low, the total amount of granite on the planet makes it a potentially enormous source of energy. To put it in perspective, 1 gram of granite stores 50 times more energy than a gram of coal. But uranium isn't the only option. There's thorium, an element 3 times more abundant than uranium and with several advantages. It's easier to extract, generates less radioactive waste, and is also much less suitable for making nuclear weapons. Finally, breeder reactors can dramatically multiply our nuclear fuel reserves. Unlike traditional reactors, which rely on scarce uranium-235, they can use much more abundant materials like uranium-238 and thorium-232. Although these elements don't directly serve as fuel, inside these reactors they can be transformed into materials that generate energy. This is key because in traditional reactors, most of the uranium goes unused. In fact, 95% of the spent and discarded fuel remains unused uranium-238, while only 1% is uranium-235 that actually produced energy. With breeder reactors, we can take advantage of that 95% and multiply the available fuel up to 140 times.
That is, if we combine all of the above, there is more radioactive material than we could consume in our entire lifetime and that of future generations, even if we maintain the current rate until the last day of the planet. So, in our hypothetical scenario of 13,400 nuclear power plants, the energy supply would be more than secure. How long would it take? And perhaps you're now wondering, how long will it take us to reach 100 billion inhabitants if we start having more children?
Let's suppose the world changes and now robots and artificial intelligence work for us. And we just have to dedicate ourselves to enjoying life. And people start having more babies, and many of them earlier. A conservative estimate of 2.5 children per woman and generations of 30 years would take 340 years to achieve this. But if we liven up the party a little and each woman has 4 children with generations of 25 years, we could achieve this in less than a century, in about 91 years. It all depends on how much effort we put into it. So, with good planning and continuing with technological advances, we can accommodate 10, 20, 50, or even 100 billion inhabitants without compromising quality of life. Plus, with a population 12.5 times larger, this channel would already have more than 11 million subscribers, and I would have already been awarded a nice diamond plaque. So go ahead, get procreating.